Hi, I'm JJ Brown with Group 4, and we'll be testing 3 experiments to verify Pascal's law. Pascal's law states that if you apply a pressure to the outside of a container of fluid, that pressure is then distributed evenly all throughout the inside of that fluid.
Now we're gonna start the first one.
Part of Pascal's law states that pressure is distributed equally all the way throughout a system. So when we had our bottle with a matchstick inside, the matchstick had a small pocket of air inside of it that kept it floating near the top. When we squeezed the bottle, we increased the pressure inside. That pressure decreased the size of that air bubble and caused it to sink. Just like you have a smaller balloon, it's not going to float as high as a bigger balloon.
When the bottle is pressed, the matchsticks will sink. And then when it's let go, the matchsticks will rise again.
This happens because the matchstick keeps and traps a bubble of air inside of it. When you squeeze the water that it's in, that pressure then condenses that little bubble of air so it's less buoyant and sinks to the bottom. When you release it, there's no longer that pressure on it, so the bubble expands again and, like a balloon you just filled up, rises to the top of the water.
A real-world application of this experiment is hydraulic brakes. As the piston applies a pressure to these brakes, the pressure is then distributed evenly to all 4 tires, causing the car to stop evenly and quickly.
And now we're gonna start the second one.
Our second experiment is called the bottomless bottle. We will fill this glass bottle up with water, and when we apply a force to the top, it will then magnify the force on the bottom because the area on the bottom of the bottle is greater than the area on the top of the bottle. So according to Pascal's law, that means that there will be a greater force applied to the bottom of the bottle, which will then cause the bottom to break and keep the top intact.
At every point inside this bottle, if we apply a pressure, it's the same at every point. Every pressure at one spot is equal to the pressure in the second spot. Since pressure is defined as the force in that spot divided by the area at that spot, then when you have a decent inward force divided by a small inward area here, which has to be a high pressure there. Now, since we have a smaller area on the inside where we're entering than on the bottom where we're coming out, where the force is hitting there, this term is very, very big, like on the scale of maybe 10 to 100. So that force will be 10 to 100 times stronger. So you think hitting glass with a hammer normally breaks it, 100 hammers at once, probably going to crack.
According to Pascal's law, when I apply a force to the top of the bottle, because it has a smaller area, the force will magnify and cause the bottom of the bottle to shoot out.
The way that we magnify this force when looking at this is when you hit the top, it applies that force and distributes it across an area, creating a very large pressure because you're dividing by a small amount. When it widens down to here, you take that same high pressure and multiply it by this large area. So now you have a huge force across the whole thing. So when he hits it, you hear that popping noise. It creates a pressure wave that goes all the way through, comes down to the bottom, hits the glass, and boom, cracks.
That's pretty cool. A real-world application of Pascal's law is actually hydraulic lifts. As you can see here, one side of the hydraulic lift will have a very small area, while the other side will have a much larger area, similar to what we saw in the bottle. Now, when you apply a given force downward, that force on the other side is magnified by X amount. This causes side 2 to have a much greater upward force than side 1 has a downward force, making it easier to lift very heavy objects such as cars.